subsequences summing to sevens problem. So basically, Farmer John has n cows that are standing in a row. Each cow is labeled with an integer ID, and Farmer John would like to take a photo of a contiguous group of cows where their IDs are add up to a multiple of 7. He wants to take the largest group that he can. So in the sample input, the first line is how many cows there are, and the rest of it is the integer IDs of those cows that are standing in a single line. And the answer for this case will be 5, because if he starts from cow, the second cow over here, and then takes this contiguous ranges of cows, their integer IDs add up to 28, and this is the best that he can do. Other answers that could have been possible was like if he does the 6 and 1, that would add up to 7, but the length is smaller. It's only length 2, and this 14 is only length 1. So the biggest length that he can get is length 5. Okay, so before we sort of dive in for the solution, let's sort of just see how we can approach this. So we want to see whether or not like we want to add up some like numbers and then see if they're divisible by 7. So that sort of screams modular arithmetic, right? So if you guys don't know about modular arithmetic, let's just go over some really quick examples. So there's this rule that if we do addition in mod, that basically if I have two numbers, let's say a plus b, and if I do this mod 7, right? And I guess we can also talk about what the word mod means, right? So what mod means is just like what's the remainder when I divide by this number, right? So if I do like, for example, 4 mod 3, or sorry, 4 mod 7, we're just saying like what's the remainder when I divide 4 with 7s, right? So that would be 4, and then 7 mod 7 is 0, right? And then let's say like 15 mod 7 would be equal to 1. Okay, so just what's the remainder when I divide by this number is essentially what mod is. So we know that something is divisible by 7 if their remainder is 0, right? So if we do like n mod 7 is equal to 0, then we know that n, so if this happens, then n is divisible by 7, right? Okay. Just when the remainder is 0, like a number is divisible by 7. So this is like sort of what we're going to be looking out for in our problem. Okay. And then there's another rule for modular arithmetic that if you add two numbers, right? So let's say we have two numbers a and b, and then mod 7. This is actually equivalent to just saying a mod 7 plus, let me put these in parentheses, plus b mod 7, and then this mod 7, right? So what this means is that we can actually like mod the two numbers before, right? Let's say that a and b were like bigger, like some huge numbers. We can actually mod them and then add them and then take the mod after, and then they will be the same result. So I mean, just like example is, let's say that I have 36 plus let's say 34, right? This would be equal to, right? So if I do this mod 7, fix the spacing because consistent. This we know is 36 plus 34 would be 70, and 70 mod 7 is 0, right? But we could have also done something like 36 mod 7 first, which would be, and then plus 34 mod 7, which would be equal to, what is this? If we just do the formula over here, right? So this mod 7, so 36 mod 7 is just 1, right? So that'd be 1 plus, this would be 6, right? 6 mod 7, and then if you do mod 7, this would just be 0, right? 7 mod 7 is 0. So we will get the same answer. This is not a formal proof, but I guess this is just an example with numbers, so it's less abstract. Okay. Um, I claim that this also works with subtraction, and this also works with um, um, what is it, multiplication as well. This is sort of, you're just going to have to trust me for this, but let's just say that this also works with subtraction. So it works for addition and it also works with subtraction. Okay. So immediately from this sort of observation, right, we can actually simplify the original problem statement a little bit more, right? So what we want to do is essentially just find some sort of a range of IDs, right? So what we're going to be doing is we're going to have to add all these numbers, right? But because we're going to have to add all these numbers, what we can do is just like simplify the array and mod 7 everything, right? Let's actually do that. So let's first read in the input. Right, so the first input is 7. Right, so if we still need help with reading inputs, that's fine. But basically, right, so this is going to be the input, right? The first input is n, right? How many cows there are going to be? So we can read this in, and then we can create the array, and then basically we can read in all the numbers inside, right? So first line would be 7, and then after I'm just going to read each of these values inside my array. Okay. But what I actually can do over here right away is I can just take the mod of it, right? Right. So for example, this would just be 0. This would become 3. This would be 5. This would be 0. And in fact, if I actually printed out arrays toString of the array, file not found. Oh, because I'm not actually working the correct. Where is this? Test. Algorithms. Oh. Guess I don't have that many algorithms here, but we can create a file. Just call it div. Let's actually just call it div7.in. I thought I had it in this test.in, but I think they are in different places, so that's fine. If we have this as div7.in, we just replace it here, but that's what we need to submit to the website later on anyway, so I guess it's good that we changed it now. Yeah, so we'll see that our array is now changed to all the mods. And this actually sort of matters, right? Because in this question, the array can be up to like 1 million, right? And even in the problem, it warns us that we might like get to a number that's too big, right? If we are summing like numbers, too many big numbers, we might get an overflow. An overflow just means like Java can't store numbers that are way too big, right? So I think the limit for ints will be around 2 billion. Yeah, 2 billion. It's whatever this number is. Max value. Right, so it's whatever this number is, right? So it's a little bit more than 2 billion. Okay. And if our sum ever exceeds this, what happens is that let's see what happens if we do this, right? We're going to actually get some random negative number. Well, not random, but we're going to get some negative number, and that's not what we really want. So if we take care of this and say everything is mod 7, and then if we keep mod 7 when we're adding, we'll make sure that our answer will never be, or our concurrent sum will never be greater than this huge number over here. So we will not get overflows. Okay. Cool. So what should we do now? Yeah, so let's actually try, now that we've read in the inputs, let's actually try see if we can see a brute force solution, right? So, do I have paintbrush? Okay. So I have the array over here, and what we can actually do is we can change right, these to the mod versions, right? So this would be 0, then this would be 3. Okay. So I guess like the brute force solution would be to generate like all possible sums for their ranges, right? So what we can do is we can maybe start from 3 and then see like all the ranges that include 3, and then see and then see if the sum is divisible by 7, if the mod 7 is equal to 0, then we want to consider that length, and we basically just want to get the largest length, right? So let's actually try coding that, right? So Yeah. So we can start from 0 less than n, right? So this I is just going to be the pointer to the beginning, right? So for example, it starts at 0, so it's going to be pointing to 3. And then we're also going to want to keep track of a j, and then we can start this at I, then say this is less than n, and then also keep track of our concurrent sum, right? So create an answer outside. We started at 0, it's just some small value. You want to see like the largest length that we can have, right? So if we start at, let's say 3, right? The first range that we can have, including 3, is just 3 by itself, right? And that makes sense, right? Like I is 0, j is 0. So our left and right is just going to be, the left is going to be I and the right is going to be j, right? So we can say sum plus equal to a of j, right? We get the 3, and then we can take the modular of sum, right? Right, because again, like when we're adding, like we can just take the mod every time. We'll be working with smaller numbers, which is easier. Yeah, so then after we take this, then we just have to see if sum is, if the mod is 7 is equal to 0, then we know that this is a potential answer. And then we say this is the max of answer. And right, so again, I and j are the left and right pointers, right? So it would be j minus I plus 1. Okay. J minus I plus 1. I guess like another example is this 3 doesn't work, right? But let's say that well, this is not divisible by 7, but let's say that this range was divisible by 7. My I would be 0, and then my j would be 0, 1, 2, 3 would be 3, right? But the length is 4, right? So we always have to add 1, j minus I plus 1. Okay. Right, and this will give us like all the ranges, right? So this I starts from 0, but like we can also have like if I starts from somewhere else, right? It would be the same thing, and we'd do the same thing for j. Okay. If you're not convinced, you can sort of trace this out, but this is just sort of some standard code to get the subarrays, right? Contiguous subarrays. So, okay. Cool. So then after we can just print out the answer, and if I didn't make any mistakes, this should give us our final answer is correct. Okay. But then again, like a lot of the times, just getting the right answer is not enough. We need to get the right answer quickly. So to analyze the sort of time complexities, let's take a look at the bounds for this question. So n is 50,000, right? And then that's the only thing that's important, basically, right? So if n is 50,000, should I put this? If n is equal to 50,000, right? And then let's look at the operations that look like it would be the biggest, right? Which is this double loop over here. This is actually going to be around an n squared operations. So it would be around n squared operations. It's actually a little bit less, but if we wanted to do sort of analysis of how many operations, right? The first time this inner loop will have n operations, right? We're going from, when I is 0, this is going from 0 to n, so around n. And then when I is 1, there's going to be one less operation over here, right? So this would be plus n, n minus 1, n minus 1 plus n minus 2, and then so on, right, up to 1. If we look at this instance, this sort of pattern. And this is actually just going to be equal to, this is going to be equal to n plus 1 times n divided by 2, right? And then if we sort of distribute this out, this would be n squared plus n divided by 2. Right? But I'm just going to say that a rough estimate of this is going to be just that there's n squared operations, right? And if we see that n squared operations, it'll be 50,000 squared. What's that? 50,000 squared will be 1, 2, 3. Wait, this is 1, 2, 3, 1, 2, 3, 2, 3. it would be 2.5 billion, right? So if we have this would be 2.550,000 squared equal to 2.5 billion, which is larger than the 10 to the power of 8 ruler that we had, the 100 million, right? Okay. So this solution is like too slow. It gives us the correct answer, but it's too slow. So we need to try to optimize this.